Alright, so we start again. So coming back to this, what is Hessian? What are the dimensions of Hessian? 2 cross 2 in this case. If your number of parameters are n, then it will be n cross n, right. So that is a huge matrix to take care of. You need to do operations on this to figure out some things like whether it is positive semi-definite, and that becomes too much computationally expensive. We just can't handle that much if your number of parameters are like GPTs, right. 175 billion, GPT-4 is rumored to have something close to 1.7 trillion and so on. Okay. So this matrix will easily become out of hands, and we just can't do anything with it. We don't really take this second derivative approach. Instead, what we do is we talk about gradient descent. Now, what are good things with gradient descent? What are the good things with gradient descent? First of all, it is computationally feasible, right, because n to n square for 1 billion, right, it is a factor of 1 billion, that is a big one. So we use gradient descent. Now coming back to this, give me backpropagation for this. Now if you remember, I had written it in this way. While writing the update, how will you write? You will write something like W1 equal to W1 minus alpha grad J, right, and this for just matrix W1, okay, and so on. So basically I don't write it this way, that will be wrong. Exactly. So what I should write is del J by del W1, okay, right, this is how it should be. Similarly, you will have W2 equal to and so on. So now help me write these guys. Just help me write what is, so maybe I will shift this a bit up and maybe erase this, and you guys are supposed to give me del J by del W11, which is this parameter, or maybe del W1 first, okay. So give me with respect to this parameter first. Have we done this before? Have we done this before in this earlier example, toy example, okay. So what is this guy? Del J by del, you have to give me the full thing. A21 dot A21 by del Z 21 dot by del W. So can I so maybe I should be able to write this one as well, so that there is absolutely no confusion at all, right? Is this fine? What will be del J by del W2 for this guy? What What will be this thing? Which part will be common? First two, this guy comes here, and what I have here is del Is this fine? Okay. Similarly, you have to come up with, how many of you are okay with this? How many of you have derived, how many of you have written both these equations? Ek baar raise your hands. Those who have written these two equations. Okay. All right. Now, what will be del J by del W11? Same as what we have done before. How many terms will be there? 5. So, quickly give me that. Del J by del A, this guy remains common. A 1, 2, del Z. What next? Del Z 2, 1, del A1. Sure, this one. Why A1? See, this is W11. This is A1, 1. This is A1. This one. W11 is here. It's not a function of, W11 is contributing to the computation of A11. Okay. So, A11 is fine. Now, what happens? So, we will have del A11 Z1 1. Now, finally, and for the sake of completeness, I will just put this. Is this fine? You will have how many such equations? No, such equations, 4 such equations, right? Where will they differ? No. So, you have to tell me how will this guy look like? Which part will be common? So, W12 is which one? X2 to A1. So, W12. This is analogous to W11 except that, okay. So, is this contributing to Z1 as well? Right. So, this whole thing comes as it is. What will be this guy? Del Z1 1 by, fine. You have to notice if I make any mistakes. Now, what will be del J W21 for example? Huh? So you have to give me, starting this is the first. So, how many of the first will remain? First 2 will remain or more? First 2. Why so? Because here you will have A2. Okay. So, in this case now, you will have this part common and this guy will change to A2. You will have A2 here, Z2 here, Z2 here and then W21. Right? And you can keep on filling such matrices. Okay? Okay, so you have to help me vectorize this now. I'll talk about Hessian a bit later. Yes. You have to help me vectorize this now. So, okay, have you computed these two matrices? Have you computed these two matrices? Right? How many elements will they have in total? This plus this, how many partial derivatives? 6, right? So there are 6 partial derivatives here. How will you write the equation for update? I'm repeating what I just erased. W1 equal to W1 minus alpha del J by del W1 and so on for second one and whatever. Okay. If I bring in B's here, will that make any difference? No, right? B1 will still look something like same as this one. You will have last thing. You will have last thing equal to 1 there. This last term will be 1. Okay. So this is all fine. Or I mean, keep B's here. There is no harm keeping that here. So this is fine. Now you have to tell me how do I vectorize this. या partial derivative से आज बोर हो गए हो? So let's do one thing. You go and redo all these calculations. Make sure you understand them. Okay, and we'll start from here in the next class, right? Because I don't want to do 2 hours of partial derivatives. Now next. But vectorization is the essence of everything in deep learning. Unless you vectorize, you won't be able to run it efficiently on GPUs, and if you can't use GPUs, don't train. Alright, let's start with this. So you have to help me figure out what is Taylor series. I don't remember. So Taylor series is what? So Taylor series is something like f of I can write this as, or maybe what I'll do is I'll use the full board. Yes. So f of x plus delta x can be written as, for one variable case. No. 1? Why 1? See, you can, Taylor series says you can write a function, right, in terms of its derivatives. Okay. How will those derivatives be written? So f of x plus delta x will become, let's say, something, check for this first term, right, plus f prime x delta x right, plus delta x square, this one, and then you will also have factorials. Okay, I mean there was of course 1 here, plus what will be the delta x cube and you just keep on doing this. So just for the sake of completeness, let us write what will happen at the kth term. Is that fine? And this is a infinitely long series. Okay? And we say gradient descent comes from this equation. How? Yes. See, it says if you make a very small change in the input for fx, right, then fx can be written like this. This change, the value at x plus delta x can be written like this. Will this give you, and this gives you with infinite precision, right? This is an infinite series, you keep on plugging this. The more terms you have, the better is the approximation to f of x plus delta x. Questions here? So what are we trying to do in deep learning? What are we trying to do in deep learning? So first of all, we are working with those cost functions which are differentiable, right? All these, in fact, this assumes something greater. What is it? This particular fx is infinitely differentiable. That means you can keep on differentiating this infinite times and it will still be a differentiable function. Okay? So, tell me where is gradient descent sitting here? What is it that we are looking for? See, this is, so this is my coordinate. I am into WB plane now, that same thing that we have been discussing. I am here at W comma B. What do I want to do? So I won't do this right now because I'll do it for vectorized form. Right now I'll just state it. Right. In fact, vectorized form also I won't write separately, I'll just change this. So, change in x, what will be the value of function there? It will be this. This gives you with infinite precision. What we are saying here is, if delta x is small, so small such that delta x square is negligible. So we can basically put the square term and the later terms equal to 0. If delta x square is, we are assuming to be 0, then delta x cube will also be 0 and keep on doing this. Okay? So all these terms will be 0 in that case. What you are left with is this. Can somebody do me a favor? Check whether this is fx or not. Just look online. Huh? It is fx, right? Huh? Right? So this is what we have. Now, how is this particular term helping us? So we are saying this. So now let me make it vectorized. Okay. So now if x is not just one variable but is a vector like we have in deep learning. Okay. So for the time being I will assume that this vector x is same as our WB. Okay. So how will you write the vectorized form? This will not be prime anymore. Plus what will happen? Delta x dot okay. Now delta x is your vector, del f is your vector, this must be a transpose. Is this fine? What will happen to the next one? Even though they are supposed to be 0 anyway. What will happen to the next term? Can I simply do delta x square? What will be this term? It will be delta x del 2 f delta x. Of course, by factorial 2 will be there. How do I change this guy? Where do I put transpose in this case? See, this is, so this is a column, this is n cross 1, this is n cross n, this is n cross 1. Where do I put the transpose? If I make this transpose, what I will have is 1 cross n, this gives you 1 cross n, n cross 1 will give you a scalar, and that is what this quantity is, right. Similarly, you can write all these equations in vector form by keeping at proper places transposes and everything. Okay. What is this quantity? Okay. So we will come back, we will revisit Hessian at some point in time, be it for very small time. What is derivative helping me with? If I go from, so if let us say now x is this one, this is W, this is B, I am somewhere here. If I make a slight change, right, if I make a slight change, what is my goal? What is my goal? My goal is to reach minima. Okay. So if I am here right now, I make a small change delta x, I will get a new value of my f, and what do I want? I want that new value to be lesser than the original point. Okay. So you have to help me with this equation now, this one, because we are dropping everything that is of the order 2 and more. Okay. So you have to help me with this. What do I do now? You can help me with this. My laptop lid's off. Yes. Gradient. So what is the definition of gradient? It is the direction of steepest increase of the function. So gradient, so what is this whole thing representing? Increase. Okay, gradient is giving me the direction of increase. What do I want? Decrease. So I will take the negative of gradient. Okay, so if I am here, I make a small change theta, I am able to reduce the value of x to some extent, right? I need to go in which direction to maximally decrease it? Flush everything, start afresh. What is this thing giving me? If I make change delta x, then what does gradient give me? The direction in which maximum increase is there. Okay? So this is taking me in the maximum increase direction. What I want is, so if you see here, there is a vector. So how many vectors of the same magnitude? If you take a vector, if you take a magnitude, how many vectors can you have centered at w comma b for that magnitude? Because see, if we are doing this, we are actually doing x plus delta x, that will give me wb plus delta w delta b. This is what we actually doing. So we need to, this is a vector. Okay. Now this is a vector for whatever magnitude you take. You have infinitely many vectors, right? Which direction do I take? The direction of maximum decrease. Can you take direction of any decrease? You can, but that particular algorithm will be lesser efficient compared to the one that takes you to the maximum descent. Okay. So what you actually do is, you don't go into the direction of gradient, you go into the direction of negative gradient. Okay. So that's how you have that equation w equal to, so now this is w, this whole thing becomes my new w, right? And how much do I change? I become w plus ki jagah minus, and then this guy will be, so now we are coming to the update equation, right? So my wb will become what? wb minus, so alpha एक बार छोड़ दो, this guy becomes, so del f by del w and del f by del b. Okay. Why alpha? Yes. So why do you need this scalar now? You want to control the step size. Okay. So you want to control the step size. If you take alpha to be higher, you are going to move in this direction with a larger magnitude. If you take alpha to be smaller, you are going to go in this direction with a smaller magnitude. Say that again.
Like अगर हम alpha को 1 ही दे दें,
Okay.
तरीके से कि हटा दे उसको, तो भी वो किसी point पे जाके converge ही करेगा, क्योंकि हमने negative of gradient ले चुके हैं.
So you will be moving in that same line. But let's say if you are very close to minima, so you are here right now. If you don't have this way to control alpha, it will shoot you somewhere here. You want your step size to be in your control. Okay. Questions?
Sir, but जैसे ये देखते हैं कि gradient 0 हो जाए तो अपने stop कर देते हैं कि update ना हो. तो अगर वही equation है कि अगर alpha ही ना हो तो overshoot भी तो नहीं करेगा, मतलब नीचे भी तो नहीं जाएगा, फिर gradient एक point पे 0 हो चुका होगा.
Say that again.
कि like अगर alpha 1 है,
हाँ.
अपने देखते हैं कि अपना gradient जहाँ 0 हो जाए वहाँ update नहीं होता, फिर w parameter
Gradient जहाँ पे
0 हो जाए वहाँ पे parameter फिर update नहीं
right?
तो अगर अल्फा मेरा 1 है तो मैं डायरेक्टली ग्रेडियंट पे डिपेंडेंट हूँ, तो ग्रेडियंट एक पॉइंट पे आकर वो 0 हो जाएगा, तो वहाँ पे भी तो अपडेट नहीं होगा।
No, let's take this offline. Okay. All right. So, and we don't keep this second term because we consider them to be too small. But as you will see, in many cases you can't just ignore this, and we'll come back to those cases now. Help me write gradient descent algorithm again. What is it? For epoch 1 to 100, compute J, compute grad J, update, right? Update W equal to W minus alpha grad J, and similarly for B's. We have talked about this, we have talked about this loop, we have partially talked about backpropagation, we need to still vectorize it, and we have talked about update. So now I think we are done with batch gradient descent. Okay. Now if you have this algorithm running, how will this curve look like? This is J. How do I want this curve to look like? Something like this. This is what I want, right? In fact, ideally not just this, I want this to become flat. Now, let's say you have 10 billion examples, okay, and it takes, so you have 10 billion examples, so your M is 10 billion, okay, and let's say you are running at something like 1 million examples per second. How many seconds will it take to go through the whole data set, the training data set? 10,000, but it is 10 billion na. So 10,000 seconds, which is something like a little less than 3 hours. So let's say 3 hours. Now if you have made a mistake of this kind, let's say you have put alpha instead of 0.3, typo ho gaya and you put 3.0, let's say. When will you realize this mistake? After 3 hours, you start from here and your graph goes there, right? So you will have to wait for 3 hours, and 3 hours is nothing because these days training is running for months. So you need to wait for months, hours, days before you get to know the first change. What is the improvement on this? How can I improve my algorithm? So instead of computing J over data set, I need to talk about a smaller data set. How many of you have heard of stochastic gradient descent? Right. How many of you have heard of stochastic gradient descent? What does it do? How does this algorithm change? ये द्वार की क्लास टू मच है, बट ठीक है. यस, हाउ, ये मेरी शक्ल मत देखो. यू हैव टू टेल मी हाउ विल दिस एल्गोरिथम चेंज in case of stochastic gradient descent. What does stochastic gradient descent do? So let me help you with something. Let's say this is the complete spectrum. So let's say this is my complete spectrum. M examples versus one example. What is M example there? I use all M examples to compute my J and then grad J and then update. Right? So in my forward propagation, I use complete training data set and then I will be using complete training data set to compute backpropagation as well, even though they will be happening simultaneously, as we will see later. What is this another extreme? You need to have at least one training example to compute J, and there are so many different possibilities in between. What will stochastic gradient descent do? So be it PyTorch, be it TensorFlow, when they say stochastic gradient descent, what they actually mean is mini batch gradient descent. Because stochastic gradient descent is this: you just update on one example, right? So how will my training loop look like now? How will my training loop look like? For epoch 1 to 100, I will have some another loop here as well. For j equal to 1 to m, compute ji, j actually, okay, and then compute gradient for that particular example, update for that particular example, right? How will the graph of this new algorithm look like? आज तो शक्ल पे दिख रहा है टू मच हो रखा है. एनीवे चलो, हाउ विल दिस लुक लाइक? हाउ विल दिस ग्राफ लुक लाइक? तो अब ये तो फिनिश करो. 2 minutes. How will this graph look like? See, you will update every example. So if you are updating every example, let's say some example was good. Good in what sense? J was it matched the label. So in that case, your J will be, let's say, some value. Now in case there is a mismatch, then J will be higher. So you will see a lot of fluctuations in case of this one. But eventually after you run for long enough, they both should converge. Taking one example is too much, you never do that. Rather you take batches of 32, 64, 128, 256, 512. Right? Let's say 64. In that case, what will happen? You will compute J for 64 examples. And now this is somewhere at a better thing. So you don't update too much, but you don't update very slowly. You update every 64 examples, and again in long run this is supposed to converge to similar like batch gradient descent. We will start from here in the next class again. Okay, enough for today.